Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 18. In this lecture, we'll discuss the interference of two-dimensional waves. This topic is covered in Chapter 18 of our textbook by Surway and Jowett. Recall that in our previous lecture, we discussed the interference of waves. More specifically, we talked about the superposition of two simple or sinusoidal waves. Those sinusoidal waves were identical in every respect, except that they had different phase constants. We found that under the right conditions, we get these interesting extreme cases, and we called those extreme cases constructive interference and destructive interference. However, all the cases that we described were really one-dimensional waves like rope waves. It turns out constructive and destructive interference are most interesting when applied to two-dimensional and three-dimensional waves like water waves and sound waves. So in this lecture, we want to discuss two-dimensional waves in much more detail. Once you've understood the mathematics of two-dimensional waves, you'll see that the mathematics of three-dimensional waves is not that different. Describing two-dimensional waves requires a slightly different notation than what we're used to. To begin with, we'll describe the wave function using the letter W for wave. The wave function will depend on two spatial coordinates, x and y. Note that we're talking about two-dimensional waves now, so the energy can propagate in the x direction or the y direction. Probably a good example to consider here is water waves. Imagine the calm surface of a pool of water, and then imagine tapping your finger somewhere in the middle of that pool, generating ripples. Each molecule on the surface of that pool of water is going to have some coordinates x and y. When you generate waves, that molecule is going to be displaced from its equilibrium by some amount. That displacement is going to be measured by the function W. So W depends on x and y, and of course it depends on time. For simple waves, we will describe the wave using this function here. This function should look quite familiar to you. Note, however, that compared to the functions we saw in our previous lecture, x has now been replaced by r. R is the distance from the source of the waves to the point of interest. So in this context, there's always two important points that you need to consider. There's the point where the source is located, and then there's the point of interest, the point that we want to talk about. So imagine that we're talking about water waves. Imagine you're looking down on the pool of water, and imagine that you're tapping your finger right here, generating ripples that then propagate outwards. So these circles represent the wave fronts. The source is where you tap your finger. That's where the waves originate. We're going to refer to the coordinates of this point as x sub s and y sub s. So the source, the S denotes, refers to the source of the waves. Now there's going to be a second point. That's the point we want to talk about. We want to talk about the molecule at some arbitrary point here, and we want to know what its displacement is. The coordinates of the point of interest are going to be denoted by x and y. The distance between the source and the point of interest is r. To calculate r, you can just use the Pythagorean theorem. You can take the coordinates of the source and the coordinates of the point of interest, subtract them, and that essentially gives you the two legs of the triangle that I'm drawing here. It's going to be a right triangle, so then you can apply the Pythagorean theorem and figure out what this distance is. I should also mention that in general, A could depend on position. For two and three-dimensional waves, A is usually a diminishing or decreasing function of R. However, that's a complication that we don't need to consider here. So going forward, we will approximate R, we will approximate A as if it is independent of R. So approximately, we will say that A is constant. It turns out the points that we want to really discuss are independent of A, so this approximation will not make much difference in our subsequent discussions. So now that we know how to describe a single two-dimensional wave, let's talk about two-dimensional waves. Specifically, we want to talk about the interference of two-dimensional waves. The picture that you should have in mind is shown here. You should imagine one source generating waves, let's say at the origin, and then a different source located somewhere else, let's say here, simultaneously generating its own waves. So now we have two waves that are simultaneously present in the same medium, and we want to know what happens when these two waves are combined. The wavefronts will propagate in every direction. A little more specifically, we want to know what happens at some point of interest, let's say over here, when these two wavefronts meet at this location. Notice that the point of interest is some distance r1 from source 1 and some other distance r2 from source 2. So what we're talking about here is the superposition of two-dimensional sinusoidal waves that have the same amplitude, they have the same wavelength, they have the same frequency, but they have different phase constants and they are at different distances from the point of interest. Mathematically, we're going to describe the two waves by W1 and W2. W1 and W2 are both simple sinusoidal functions in two dimensions. Notice that the two waves have the same amplitude, they have the same wave number and therefore the same wavelength, they have the same angular frequency and therefore the same frequency, but they have different phase constants and they are at different distances to the point of interest. When these two waves meet at the point of interest, the resultant, their superposition, is simply the sum. We're going to denote the resultant using the letter W, and we're going to say W is simply W1 plus W2. You can add these two functions together using the same trigonometric identity that we've seen several times now. The so-called sum to product identity allows us to combine these two sine functions and write it as this enormous function down here. As you look at this enormous function here, you notice that there is the typical sine function, and the sine function depends on position, and it also depends on time, and it has some phase constant. So this portion simply represents the oscillating part of the wave. Everything else that's in front, to a cosine of this enormous argument, is simply the amplitude. Our goal now is to analyze this cosine function. The behavior of the cosine function will tell us what the amplitude will be, and then we can discuss those extreme cases that we're interested in. We'll want to know when this cosine function is equal to 0, or when this cosine function is at its optimal value of plus or minus 1. Before discussing the constructive or destructive interference of two-dimensional waves any further, we need to simplify the notation a little bit. You may have noticed that the final function that you saw on the previous slide was quite a lengthy and complicated function. It's difficult to analyze such functions unless we simplify the notation a little bit. Discussions of interference can be simplified if we introduce the notion of total phase. The total phase of a sinusoidal wave is basically everything that's inside the parentheses. So recall that for two-dimensional waves, we're basically using this function to describe them. Everything inside the parentheses is referred to as the total phase and denoted by the capital Greek letter phi. Note that phi depends on time, but it also depends on r. And of course, r secretly depends on x and y. So we can say that everything inside the parentheses, the total phase, is itself a function of x, y, and t. It's the total phase that determines the value of sine. So the total phase is interesting to us because by knowing what the total phase is, we can figure out what the value of the sine function is, and that in turn tells us what the value of the wave is. The terminology here is a little confusing. Do not confuse the total phase with the phase constant. The total phase is denoted using capital Greek letter phi. The phase constant is denoted using lowercase phi. The phase constant, as the name suggests, is really just a constant. The total phase, on the other hand, is not a constant. It depends on x, it depends on y, and it depends on t, so it's really a function of 3 parameters. Now that we're familiar with the concept of total phase, let's repeat our discussion of interference in terms of this simplified notation. So once again, consider the superposition of 2 simple waves. They're identical in every respect, except that they have different phase constants. Wave 1 was a sine k r1 minus omega t plus phi 1. We're now going to write that as a sine phi 1. In other words, everything in the parentheses that you see here, k r1 minus omega t plus phi 1, has now just been abbreviated as capital phi 1. So think of phi 1 as a complicated function that depends on t, and it also depends on x1 and y1. And then everything inside the parentheses of the second wave has been also abbreviated as phi 2. We can now say that the sum, or the superposition of these 2 waves, can be expressed simply in terms of this function here. We're using the same trigonometric function that we used in our last lecture to go from a sum of sinusoidal to the product of sinusoidals. Written in this form, we can more easily talk about interference. Notice that the function on the right has phi 1 plus phi 2. There is a time dependence in here, and therefore the sine part is the oscillating part of the wave, but everything else is independent of time. It does not depend on time, so we can think of this entire thing as the amplitude. Thinking of this entire thing as the amplitude, we can now talk about when this cosine function is equal to 0 and when it is equal to its optimal value. So now we want to discuss the precise behavior of the amplitude of the superposition of the resultant. More precisely, we want to know what the cosine function is doing. Remember, the cosine function has a couple of extreme cases. Sometimes it's equal to 0, and then sometimes it takes its optimal values of plus or minus 1. When is that cosine value equal to its optimal value? Well, the answer is when the argument is equal to some integer times pi. Now notice that we're dividing by 2, so we want the numerator to be some even number times pi. If the difference between phi 1 and phi 2, I'm calling that delta phi, is something like 100 pi, then that divided by 2 gives us 50 pi, and cosine of 50 pi is equal to plus or minus 1. That's a case where the 2 waves are constructively interfering with one another. They help each other out, they reinforce each other to give us a resultant that has a maximum value. We can also talk about the case where the cosine is equal to 0. That happens when the numerator, delta phi, is equal to an odd number times pi. If delta phi, for example, is equal to 9 pi, then when you divide that by 2, what we get is 4 1/2 pi, and cosine of that will be equal to 0. When the cosine term is equal to 0, the amplitude is equal to 0, and therefore the entire wave is equal to 0, we refer to that as destructive interference because the 2 waves are basically canceling each other out. They're essentially destroying each other. Notice that the discussion on this slide is quite familiar to you. It resembles a very similar discussion we had in our last lecture. The only difference is that the phase constants have now been replaced by total phases. We can summarize our discussion thus far as follows. We're interested in the superposition or the combining of 2 waves. These are two-dimensional waves, so they're a little more complicated to write, but thanks to the notation of the total phase, we can write them simply as A sine phi 1 plus A sine phi 2. Note, however, that phi 1 is really a complicated function that depends on the parameters k, omega, and the phase constant. It also depends on x, y, and t. W here is the resultant wave. The sum of these two can be written as the product of two sinusoidal functions. When the cosine function takes on its optimal value, we can say that the resultant has its maximum amplitude. That happens when the numerator is basically equal to an even number of pi's. It doesn't matter if it's plus or minus. The point is that the cosine function takes its optimal value, and so the displacements as dictated by the amplitude are going to be the biggest. We get destructive interference when the difference in the phases is an odd number of pi. That's when this cosine function basically becomes 0, and so the entire resultant is going to be 0. This is the case of minimum amplitude. This is the case where the two waves have essentially canceled each other out. So we've covered a lot of new material. Let's do a practice problem to help us digest some of this information. We have two identical sources shown below, and they create waves with a wavelength of lambda. What type of interference is there at point 6, 0? So we have two sources. One of them is located here and the other one's located here. Each one is generating its own waves. The two waves are located at different distances from some point of interest. In this particular problem, the point of interest is 6, 0. So if these are water waves, we want to know exactly what happens at this point when these waves arrive at this location. These could also be sound waves. For example, you might have two audio speakers simultaneously generating sound waves, and we want to know what a person would hear if the person were standing at coordinates 6, 0. When these two waves arrive at this location, their superposition is going to result in some kind of interference. It might be constructive interference, or it might be destructive interference. It could also be partial interference. Partial interference refers to the superposition that's neither constructive nor destructive. To be honest, partial interference is simply not that interesting. It's the extreme cases of constructive and destructive interference that are most interesting in terms of applications. Now, to analyze this problem or to be able to answer this question, we need to know something about the total phases. We have two waves, and each wave will have its own total phase. Recall that the total phase was defined as everything that's inside the parentheses. So the total phase, capital Phi, is equal to K R minus omega t plus phi. Of course, K is 2 pi over lambda, so you can write this as 2 pi over lambda times R, and omega, of course, is 2 pi over the period times t plus phi. So this is simply another way of writing the total phase. Once again, do not confuse lowercase phi, which is the phase constant, with the uppercase phi, which is the total phase. Total phase for wave 1 is going to be 2 pi over lambda R1 minus 2 pi over the period times t plus phi. Similarly for the second wave. Notice that in this particular case, the two waves have the same phase constants. They have the same phase constants because we're told that the two sources are identical. So you're going to encounter this phrase quite a bit, identical sources, and you need to understand what it means. What that means is that these two sources are essentially doing the same thing. For example, if these are two audio speakers, then the two speakers are essentially playing the same music, the same frequencies, the same notes at the same time. If these are water waves and you're simply tapping your finger, for example, on the surface of a pool of water, then you're tapping one finger here and another finger here, and those two fingers are doing exactly the same thing at the same time. So we can say that they have the same phase constants, they have the same periods, they have the same wavelengths. What's different is R1 and R2. Incidentally, I've chosen to write the phase constant in this form because the problem gives me the wavelength, so I'm trying to express everything in terms of known parameters. Now recall that the type of interference you get depends on the difference between these two phase constants. If the difference between phi1 and phi2 is an even pi, I'm going to get constructive interference. If it's an odd pi, I'm going to get destructive interference. And if it's something else, neither even nor odd, then I'm going to get partial interference. That's the most common case, but it's also the least interesting case. If you take the difference between phi1 and phi2, you'll see that the phase constants will cancel. The terms with time in them also cancel, and what you're left with is 2 pi over lambda times R1 minus R2. Or if you prefer, you can also write R2 minus R1. The difference, of course, is a minus sign. Remember that in this context, we don't care about the minus signs. Now you need to calculate R2 and R1. You can read off the locations of the two sources and the point of interest from the graph, and then you can calculate R1, then you can calculate R2 with a little bit of geometry, and then you can calculate the difference between them. When you do, you find that 2 pi over lambda times delta R is 21.991157. You can verify for yourself that this bizarre number here is actually 7 pi. In other words, if you take this number here and you divide it by pi, you'll get 7. This is important to us because I can now see that the total phase difference is equal to an odd number times pi. Since we have an odd number times pi, we can say that the interference is going to be destructive. If this number had turned out to be, let's say, 22 times pi, we would say that's an even pi, and therefore the interference was going to be constructive. In this case, however, we have destructive interference. When these two waves arrive at the point of interest, they're going to destroy each other. If these are two audio speakers and you happen to be standing at this point, what you will hear is silence. For later reference, we should also note that R1, the distance from source 1 to the point of interest, is equal to 6, which just happens to be 11.6 times the wavelength. R2 happens to be 15.1 times the wavelength, and if you calculate the differences between the R's, you'll notice that it is approximately equal to 3.5 times the wavelength. This is going to be important for us later because it gives us a shortcut to figuring out when we have constructive or destructive interference. The method that I have suggested so far is to calculate the difference in the phase constants and look at whether it's even pi or odd pi, but soon you will see that you can also look at delta R, and if it's a whole number times lambda, then you have constructive interference. If it's a half integer, half of a whole number times lambda, then you have destructive interference. Our last practice problem was about identical sources. Identical sources of waves are quite common, and so we need to have some specialized knowledge about them. Consider two identical sources in 2 or 3 dimensions. We want to know how they interfere. Of course, interference is all about delta phi, the difference in the total phases. We know that if that is equal to an even number of pi, then we get constructive interference. We can express that in a mathematical language and say that when delta phi is equal to 2n pi, we have constructive interference. As we saw in the previous practice problem, delta phi can be expressed as 2 pi over lambda times delta r. So when this whole quantity is equal to 2n pi, we have constructive interference. Now looking at this equation, you can see that this 2 cancels this 2, and this pi cancels this pi, and I can bring the lambda to the other side. And I find that the condition for constructive interference corresponds to this particular condition here. When delta r is equal to n lambda, an integer number of lambdas or a whole number of lambdas, then I have constructive interference. We also know that we get destructive interference when the phase difference is an odd number times pi. From our previous practice problem, we noticed that delta phi could be written as 2 pi over lambda times delta r. Once again, you can simplify this a little bit. Notice that the pi here cancels the pi here. You can take this entire quantity here and divide it by 2, in which case you would get n minus 1/2. You can bring the lambda to the other side as we did before, and you find that when delta r is equal to n minus 1/2 lambda, then we get destructive interference. This is important because it gives us a shortcut for determining what type of interference we have for identical sources. Turns out for identical sources, constructive or destructive interference depends all on delta r. You don't need to worry so much about delta phi. You can use delta phi, but as you will see, calculating delta phi can be tricky in some instances, but calculating delta r usually just boils down to geometry and is much easier to calculate. When the path length difference, delta r, is equal to an integer number times lambda, we have constructive interference. When it's a half integer times lambda, like 3/2 lambda, 5/2 lambda, 7/2 lambda, then we get destructive interference. Identical sources are very common, especially in optics. So a little bit later, when we start talking about light waves, for example, you will see us use these formulas quite frequently. I want to end this lecture with a word of warning. Do not confuse your Greek letters. It's very common for students to confuse pi with lambda. Of course, they have different meanings. Lambda refers to the wavelength and is measured in meters. Pi is a very specific number, 3.141 ... and it's usually measured in radians. To better appreciate the difference between these two and also their connections, note that shifting a wave by lambda meters is equivalent to shifting it by 2 pi radians. Here's what I mean. Consider a simple sinusoidal wave, which we're denoting by the letter W. Now suppose that we shift this wave to the left or to the right, not so important at this point, by lambda meters. What that means is that we take the position variable and we basically replace it with r, let's say plus lambda. So take this quantity and place it in here. In other words, substitute r plus lambda for r, and you will see that this entire expression now can be written as follows. So the r plus lambda simplifies to this expression over here. You can rearrange this expression and then note that this quantity and this quantity and this quantity can be written simply as capital phi, and then we're left with 2 pi. So adding lambda to r is the same thing as adding 2 pi to the phase constant. This is ultimately the root of the confusion between pi and lambda. You're basically choosing to talk about radians or meters. You're choosing to talk about pi's or lambdas. They're related, but they're not exactly the same thing. Another way to say the same thing is to say that 2 pi radians is basically lambda meters as far as waves are concerned, or 1 cycle is equal to 1 wavelength. Armed with this information, you can now look at interference two different ways. When you're talking about constructive and destructive interference, you can either calculate the phase difference, that's delta phi, or you can calculate the path length difference. By path length, I mean, of course, R2 minus R1. If you're going to analyze the problem in terms of the difference in phase, then you need to talk about even pi and odd pi. But if you're going to analyze the problem in terms of delta R, then you need to talk about integer lambda and half integer lambda. So this first column and the second column, they're both giving you the same information. It's just that one of them is in terms of pi and radians, whereas the other one is in terms of lambda and meters. And that is the end of this lecture. Thank you for your attention.